So let's take the second example. We are going to solve the differential equation y prime prime plus y equals cos x using the method of variation of parameters. Let's try this example together. So we have the differential equation y prime prime plus y equals cos x. So first we are going to generate the corresponding homogeneous differential equation, that is y prime prime plus y equals 0, and then we obtain the auxiliary equation m squared plus 1 equals 0. Now we can transpose 1 to the right hand side so that we have -1, and then we try to take the square root of both sides so that we have m equals, now square root of -1 is plus or minus I, so plus or minus I, and that is equal to alpha plus or minus I beta. Therefore we have alpha equals 0, that is by comparing you have alpha equals 0 and then you have beta equals 1. So the general solution to the homogeneous differential equation yc is given by e to the power alpha times x or times c1 cos beta x plus c2 sine beta x. So thus we have yc to be equal to e to the power, now alpha is 0 times x, now 0 times x is 0, and then e to the power 0 is 1. So we are going to have 1 times c1 cos beta is 1, so 1 times x is x, so c1 cos x plus c2 sine x. So this is the solution to the corresponding homogeneous differential equation. Now since we have yc, let's try to find the particular integral, which is yp. Now yp on the other hand is given by u1 y1 plus u2 y2. Now first of all we need to establish that y1 is equal to cos x, and then y2 is equal to sine x, and then we have g of x equal to cos x. Therefore, to find u1 and then u2, we first of all need to find the wronskian. So the wronskian of the two functions y1 y2 is given by, now we have y1 to be cos x and then y2 sine x. So when you differentiate cos x you have negative sine x, when you differentiate sine x you have cos x. So that is equal to, we multiply cos x by cos x, we have cos square x minus negative sine x times sine x, that is negative sine square x. Now we can simplify this as cos square x plus sine square x, and then according to trig identities we know that cos squared x plus sine squared x is equal to 1. Therefore we have the wronskian to be equal to 1. Now let's try to find u1 and then u2. So we have u1 equal to negative the integral of y2 times g of x divided by the wronskian times the x. So that is equal to negative the integral of, we have y2 as sine x, and then g of x to be cos x divided by 1. Okay, so it's actually the same thing, and then dx. Now to integrate this function we are going to use u substitution. So first we say let u be equal to cos x, and then we want to differentiate u with respect to x, so we have du dx, and that is equal to negative sine x. Now let's try to make dx the subject. So we have dx to be equal to, we interchange the positions of these two, and then we have negative du over sine x. So this is u and then this is the x. We are going to plug them in here. So we have u1 equals negative the integral of sine x times cos x, which is u, so times u, and then times dx, which is negative du over sine x. So sine x cancels out sine x. We are left with u1 equals negative the integral of u du. So with this negative becomes positive, and then we want to integrate u with respect to u, so that becomes u squared over 2, and then we ignore the constant of integration. Therefore we have u1 to be equal to, now u is cos x, so that gives cos square x over 2. So this is u1. Now let's try to find u2. So you know u2 is given by the positive integral of y1 times g of x divided by the wronskian times dx. Now this is equal to the integral of y1 is cos x, so cos x times g of x is also cos x, so cos x times cos x all divided by 1 dx. So we are going to have u2 equals the integral of cos square x dx. Now using the power reducing formula, you are going to obtain the integral of 1 over 2 times 1 plus cos 2x dx. Now if you use the formula cos a plus b, that is equal to cos a cos b minus sin a sin b, you are going to obtain 1 over 2 times into bracket 1 plus cos 2x. That is the power reducing formula. Now let's try to pull out the constant 1 over 2. So we are going to have 1 over 2 outside, the integral of 1 plus cos 2x all dx. Now let's integrate one after the other. So when you integrate 1 with respect to x, you have x plus, when you integrate cos x, you have sin x. So this becomes sin 2x, and then you are going to differentiate 2x with respect to x, and then you have 2. So we have this divided by 2. So thus we have u2 equal to 1 over 2 times into bracket x plus sin 2x over 2. Now we know that the particular solution or the particular integral is given by yp equals u1 y1 plus u2 y2. So let's plug in the expressions for u1 y1 u2 and then y2. So we have u1 to be cos square x over 2, and then y1 to be cos x. So that's cos square x over 2 times cos x plus, for u2 we have 1 over 2 into bracket x plus sin 2x over 2 times y2, and then we have y2 to be sin x, so times sin x. So let's try to simplify this. So from the trig identities, we know that cos square x, we know cos square x plus sin square x is equal to 1. So what this primarily means is that cos square x is equal to 1 minus sine square x. Again, for sine 2x, we can have sine x plus x, and that is equal to sine x cos x plus cos x sine x. So we have sine 2x, and that is equal to 2 sine x cos x. So let's plug in the expressions for cos square x and then sine 2x in here. So for cos square x, we have 1 minus sine square x over 2 and then times cos x plus 1 over 2 into brackets x plus 2 sine x cos x over 2 times sine x. Now let's simplify further. Here we are going to multiply cos x across to the left, so that becomes cos x minus sine square x cos x over 2 plus, now here you can cancel out 2, so that you have 1 over 2 on the outside, and then you multiply sine x across, so you have x sine x plus sine square x cos x. Now notice that 1 over 2 affects each of the terms in here, so we can simplify this as cos x minus sine square x cos x plus x sine x plus sine square x cos x all over 2. Now here we have negative sine square x cos x and then positive sine square x cos x, so we can cancel out these two, and then we have yp to be equal to cos x plus x sine x over 2. So this is yp. Now we know that the general solution is given by y equals yc plus yp. So we have yc to be equal to c1 cos x plus c2 sine x. So c1 cos x plus c2 sine x, and then plus yp. Now we can express yp as 1 over 2 cos x plus 1 over 2 x sine x. Now we have cos x here, cos x here. C1 is a constant, 1 over 2 is a constant. So let's say C1 plus 1 over 2. Let's call that C3. So we have y to be equal to C3 cos x plus C2 sine x plus 1 over 2x sine x. Now let's take example 3. So for example 3, we are going to solve the differential equation y prime prime plus y equals cot x. Now you realize that the left hand side of the differential equation is similar to what we had for example 2. So that's y prime prime plus y equals cot x. Now what this primarily means is that the general solution to the corresponding homogeneous differential equation is given by c1 cos x plus c2 sine x, similar to what we had in example 2, and thus we are going to have y1 to be cos x and then y2 to be sine x, and therefore we are going to have the wronskian to be equal to 1, similar to what we had for example 2. So the wronskian is equal to 1. Now notice that we have g of x this time to be cot x. G of x is equal to cot x. So the next thing we are going to do is basically to find u1 and then u2. So for u1, that is given by negative the integral of y2 times g of x divided by the wronskian times dx. So that is equal to, we have negative the integral of y2, that is sine x, so sine x, and then we have g of x to be cot x, so cot x dx. Now cot x is equal to cos x over sine x, so we have cos x over sine x dx. We cancel out sine x and then sine x. Now we want to integrate cos x, and that is equal to sine x. Ignoring the constants of integration, we have u1 equals negative sine x. So this is u1, negative sine x. Now let's move on as we find u2. So for u2, that is equal to the positive integral of y1 times g of x divided by the wronskian. So we have y1 to be cos x times g of x is also cot x. So cot x is cos x over sine x dx. So this gives us we have u2 equals the integral of cos square x over sine x dx. Now we know that cos square x is equal to 1 minus sine square x. So we have 1 minus sine square x over sine x dx. So we can express this as 1 over sine x minus sine square x over sine x. So sine x will cancel one of the x's here, one of the sine x's here. So simply we can write minus sine x or dx. And then notice that 1 over sine x is equal to cosec x. So we have the integral of cosec x minus sine x or dx. Now, if you integrate cosec x, then we are going to get ln of tan x over 2. And then when you integrate sine x, we are going to get negative cos x. So negative becomes positive, and then cos x. So this is u2. Now we know that the particular solution yp is equal to u1 y1 plus u2 y2. Now we have u1 giving us negative sine x, so negative sine x, and then y1 is cos x, so times cos x plus, now we have u2 also giving us ln of tan x over 2 plus cos x times y2 is sine x, so times sine x. So let's simplify further. So yp is equal to negative sine x cos x plus, now we are going to multiply sine x across, so that becomes ln of tan x over 2 sine x plus cos x sine x. Now we have negative sine x cos x, positive cos x sine x, so you can cancel out these two, and then we have yp to be equal to sine x times ln of tan x over 2. So this is the particular integral or the particular solution. Therefore, we have the general solution to the given differential equation, y to be equal to, we have c1 cos x plus c2 sine x plus sine x times ln of tan x over 2.